When an earthquake strikes a city, seismic energy tears through the layers of soil buried deep underground, warping and compressing the earth long before the shaking ever reaches the surface. Soil possesses a complex physical duality. Under light vibration, it behaves like a rigid, solid block. But when subjected to the intense, chaotic force of a seismic wave, it softens, absorbing and dissipating the incoming energy like a dense sponge. Engineers define this as nonlinear behavior. The soil lacks a single constant structural identity. Its stiffness and its ability to dampen energy are shifting every moment the ground is in motion. Attempting to track these shifting properties mathematically creates a massive data bottleneck. To map the soil state every millisecond, the calculations multiply exponentially, resulting in a cluster of data points that would overwhelm most conventional processing power. To bypass this computational wall, engineers utilize a specialized software called Shake. Rather than attempting to track the chaos in real time, Shake employs an algorithmic loop to find a simplified, workable solution. The strategy requires a trade-off. By moving away from millisecond by millisecond tracking, engineers can build a stable, calculable approximation of how the ground will actually behave. The process begins with a baseline guess. The algorithm starts by assuming the soil is at its maximum potential stiffness, the state it occupies before the earthquake even begins. Using this rigid baseline, the software runs an initial simulation, passing the earthquake wave through the model to see how the layers react. This initial pass reveals the maximum strain, the absolute peak of physical deformation the soil layers experience during the simulated event. However, this peak is an outlier. Because that extreme deformation only exists for a tiny fraction of a second, using it as the standard for the entire earthquake would result in a model where the soil is calculated as far too soft. To find a more representative value, the software applies a constant scaling factor. It takes that maximum peak and reduces it to 65% of its original value, a metric known as effective strain. This 65% adjustment creates a stable middle ground. It produces a value that captures the intensity of the shaking without being skewed by a single momentary peak that doesn't reflect the earthquake's overall impact. Now the update phase begins. The software uses the effective strain to adjust the model. It mathematically lowers the stiffness of the soil and increases its damping or energy absorption to match the intensity of the strain. The software then reruns the exact same earthquake simulation from the beginning. But this time, it uses these softer, more absorbent soil properties. After the second pass, the algorithm performs a logic test. It compares the soil properties it used as the input to the properties that resulted from the simulation. At this stage, the two sets of numbers do not match. Because there is still a discrepancy, the software triggers another loop. It takes the new output, updates the soil properties again, and recalculates. The gap between the input and the output shrinks with every pass. This repetition continues until the system reaches convergence. This is the moment the loop breaks because the input properties and the resulting strain are finally in perfect mathematical agreement. Through this iterative process, a rigid computer program can systematically narrow down and identify a state of equilibrium within a chaotic, nonlinear system. It is important to note that the final output doesn't actually track the soil's second-by-second behavior as the earthquake progresses. Instead, the algorithm provides an equivalent linear approximation, a single static set of properties for each soil layer. This result represents the mathematical average of how the soil behaves for the entire duration of that specific earthquake. The chaotic, fluctuating reality of the event is distilled into a single, reliable value. These stabilized numbers provide the actionable data architects and engineers need. It allows them to calculate exactly how a building's foundation will respond to the simulated forces of the earth. Structural safety often depends on knowing when to step back from the impossible task of capturing every microsecond of physical reality, and instead relying on the precision of a well-calibrated mathematical compromise.